Okay, so we will continue on fractals, right. So, last time we were talking about fractals. In fact, we looked at geometric fractals, right. So, just to recapitulate some of the properties and details we discussed about fractals. So, one of the thing is that they exhibit infinite details, right. So, which basically means that if I try to zoom in to the fractal structure, I keep finding the details. So, the amount of detail which are inside the structure, truly speaking, they are at infinite level. So, you keep zooming in, you keep finding details in it. So, for the purpose of creation of these fractals, we put a limit to it because of the resources we have, computational space and whatever. So, we cannot do this at infinite level. And the other important property they exhibit is the self similarity. So, the self similarity property is again referring to the situation where one is trying to zoom in to the structure. You observe some scaled copy of the same structure when you zoom in. Right. So, there is a self similarity from what it was originally as a structure and what you keep finding as in the details. So, in fact, these two characteristics one when observes also finds in many of the natural phenomena. Right. For instance, you take a view of a mountain and you try to approach the mountain, zoom in. So, first of all you find lots of details coming out, and the second thing is the kind of structure you observe has some similarity to the overall structure. So, that is self similarity. So, many of these natural phenomena also show these characteristics. So, that is one of the reasons fractals are chosen for modeling natural phenomena. That was the motivation. So, if we go back and look at the process of their generation, so it turns out that it is a recursive procedure where you start from some initial state and you consider a transformation function, right, which could be a transformation in terms of a geometrical pattern or some other transformation, and you keep applying that transformation function. So, there is a recursive application, successive application of the same thing. So, it is a recursive procedure which is what adds the details into the structure. Right. So, the other observation we had, which was particular in the case of geometric fractals, that the process of generation is deterministic. You take a copy of the transformation and then reapply that, the same transformation. So, and it is deterministic, which in fact renders in these geometrical fractals the regularity in what the pattern gives you. Though these fractals demonstrate irregularity in their structure, but the way these get applied show a regularity in that pattern. So, there is a regularity in the irregularity. Right. So, that is because of the fact that they are deterministic in the process of the generation. And we also observed that they have a dimension like what we observe in Euclidean geometry, but this dimension is referred to as fractal dimension because of the fact that this could be fractional as a number. So, you can have a fractal dimension like 1.26, 1.89 and so on. And we also observed the effect of this fractal dimension in some sense captures the roughness of the structure which we obtain, the amount of roughness let us say, and also a self-filling characteristic. Right. For instance, we observed that when a fractal dimension goes from 1 to 2, so you can actually have a fractal dimension of 2 for a curve. Then the property of self-fillingness is observed. So, when the fractal dimension is 2, the whole area where it gets applied, it sort of self fills, which intuitively matches to the dimension what we observe as a Euclidean dimension of 2 for a planar structure. Right. So, these are some of the characteristics which we observed in the case of geometrical fractals. So, just to give you what was happening. So, again let us say looking back to the construction of von Koch curve. So, you have a pattern of this kind. So, we start from a state which was say a straight line, and this is the transformation which is applied. So, that is the transformation we are referring to as f, and then you again apply this transformation to each of these segments. So, this is what is happening, that is what the recursive procedure is, and so on. So, ultimately you get a rough pattern structure, right. This is the von Koch curve. So, now the problem with them is, as we looked at, is because of the nature of their generation which is deterministic, they exhibit the self similarity property in exact form. So, they are exactly self similar structures, right. Now, when we are referring to them as procedures for constructing natural phenomena, where we observe that there is no deterministic pattern, but in fact there is a randomness into whatever we observe, then there is a modification to this process where randomness is introduced. So, the fractals which have some randomness to it are referred to as random fractals. Okay. So, the whole idea is that the process of generation would now have some randomness in it. Okay. Which in turn renders a self similarity, but in a statistical form. Right. So, when you zoom in a fractal structure which is randomly, which has randomness in it, then what you observe that the zoom in structure is seemingly similar to the original structure, not exactly similar. Okay, so, that is what we mean by statistical self similarity. So, there are number of ways in which these random fractals can be generated, and that is what we are going to look at. In fact, one of the features of the process of generation you observe is involving some sort of a subdivision mechanism. See, adding details in some sense a method of subdivision. Then what you do at the level of subdivision is something different, but as a process you are doing some sort of a subdivision, even when we are generating these these geometric fractals. So, that is what we are going to look at. What are the various ways one can think of as a process of subdivision, which in turn gives you a generating approach. Fine. Okay. So, let us see the process of generation, and one of the ways in which one can think of generating these random fractals is a midpoint subdivision. So, let us consider an example where we are interested in creating fractal curves. Right. So, again one can start from a line A to B, which is like an initiator to the fractal, and you want to add details to this line similarly as we did in geometric fractals. So, when we are saying that it is a midpoint subdivision, so the idea here is that we would consider the midpoint of this line and do an action to that. Okay, that is why we call this as a midpoint subdivision. So, what do? We actually take this midpoint, which is at M, displace it, let us say to the point C. So, this AB line, initial AB line, now is transformed to two segments, AC and BC. Fine. Now, clearly there are issues concerning as to how much do you displace, right? What is the magnitude of MC? And the other issue is in what direction do you displace? These are the two basic issues, right? So, any suggestions to this? When we are displacing this M to C, remember that this process has to continue. Next time what will happen is I will consider this as a segment, take the midpoint here, do a displacement of that. Similarly, this segment, take a midpoint of this and displace it. So, at every level I am performing this process of subdivision and a displacement of that midpoint for that level. So, at various level this issue would arise. How much do I displace and in what direction do I displace? So, one of the things which needs to be looked at is that the displacement has to capture the level or the scale where I am, right. So, at this level this is the displacement because of the fact that this is the scaling, this is the initial length I had. So, this has to in some sense scale with this. Similarly, when I do a displacement here, this has to scale with this. And the second thing is the direction. So, direction could be, some suggest that you could actually do this displacement only in one direction, which is in 2D if considered this as x and this is y, then this is y direction, or it could be the direction of the normal of this segment. So, here it will be normal, here it will be normal here. The other, let us say, parameter to the generation is the flipping of it. Remember, we could actually go positive offset, we can also go negative offset. So, that is also additional parameter, something like a flipping what we used in the construction of dragon. So, these are the various parameters one can play with. So maybe at the end of the whole thing we get something like this. Okay. So, this seems some of interest if you are trying to use them for modeling some natural phenomena, for instance coastal line, unlike von Koch curve, which was extremely regular structure. Fine. So, I have an example of something which could be a coastal line, but the authenticity is not guaranteed. So, let us say you consider having a coastal line of this, right, where what you have done is you have supplied an initial structure, right, which gives you a gross shape. So, it is like the initiator where you want to start the generation of fractal curves, and then apply this random fractal generation on the initiator. So, you may get this, right. So, clearly this should not be confused with the exact GIS data of Indian map. But let us say if you are doing a simulation or doing some synthesis, computer generated synthesis. So, this is a fairly acceptable approximation, right. Okay. So, this was concerning the curves. A similar idea can be now used for surfaces. So, let us say we are talking of surfaces. So, in fact, there are number of ways we can look at the process of subdivision again. So, let us say you have an initiator of the kind where you divide or you construct the surface as collection of triangles, right. So, at some iteration, say n, you have a configuration like this. So, there is this triangle, there is another triangle here, okay, and you have the data for these, positional data of these. Okay. Now, there is a type of triangle edge subdivision, where you do something very similar to what you did in the case of curve, where you obtain the midpoint of each of the edges in the triangle. So, this is the midpoint, this is the midpoint, this is the midpoint, and so on. So, that becomes your next level of surface, and then appropriately do the construction of triangles using those points, right. So, basically what I mean is this. So, the next iteration, let us say n plus 1, has got these additional points which are nothing but the midpoints of the individual edges of the triangle which are there, and then you have these as new set of triangles. And this can be repetitively done. From this iteration you can go to the next iteration where you subdivide each of the edges here, and then again do a construction of set of triangles. Fine. So, let us say if we are doing this, so this is what is happening in a topological fashion, how these triangles and the points are being added. Again, at a surface construction level, you have, let us say this is the triangle to start with, this is the initial triangle, this is the these are the midpoints you had. So, because of these points, now this whole triangle becomes in 4 triangles. So, this is the topology of triangles which have been constructed. Now, you have to also do the height assignment, right. That is where the perturbation to the surface would come, right. So, what you are going to do, you are going to displace this point to a certain height, you are going to displace this point to a certain height, you are going to displace this point to a certain height, something very similar to what was done in curves, right. So, you have this height and this height. So, the new surface is this triangle, this triangle, this triangle and this triangle. Right. So, again there are issues. What are the issues?
So, the direction, the amount by which we displace in the y direction.
Yeah. So, one of the thing is the direction where you in which you displace these points. Okay. So, let us see the issues. What I am trying to refer here is, again one of them is the amount of displacement. So, amount of displacement is relevant. Let us say we go to the next level where we take this triangle and we take this triangle. So, there will be a midpoint here somewhere which would be shared between this and this, right. So, the amount by which I displace for this set of triangles has to be the same as for this, otherwise there is going to be an inconsistency. And when I am using the randomness, which is primarily obtained by some random number generator, one has to be consistent in getting these random numbers or the random heights for the two adjoining triangles, otherwise I would end up getting inconsistency. So, one may have to relate, let us say if you are using some seed based generation of random, then one has to maybe use the indices of the edge to determine the seed. It has to associate to the edge, right, so that you are consistent in the height you assign. So, similarly the direction of the displacement. So, once again if I have the midpoint here which is being shared and I displace this, let us say along the normal of this triangle and the other one along the normal of this triangle, then I am going to have a rupture, I will get a hole. Okay. So, there also you require consistency. So, one has to address the issue of consistency whenever you are doing this, both in terms of setting the amount of displacement and choosing the direction in which you displace. Fine. Okay. So, let us see some of the results. So, if you consider this as your base triangle, so this is at a level 2. So, 0 level is the base triangle, level 1 when you have 4 triangles and the level 2 is after that. So, this is the level 2 and then this is level 4 and so on. So, at the end you get something like this. It is not too bad, that is all I can say, right. It does not still look like a mountain, but it is okay. Right. So, one of the issues actually you observe here, and that is the question I am going to ask you, is that what is the rendering or let us say shading model one should be using for rendering fractals. You understood the question? What is the shading model one should be using for rendering fractals? So, would you be doing Fonck shading, or would you be doing Groth shading, or would you be doing flat shading? Any idea? Okay, so let us say I give you the answer. The answer is that you should be using flat shading. Tell me why. Okay, not getting anywhere, huh? Say you were using here Groth shading or Fonck shading. What kind of result you would have had?
So we want
Yes.
to see this difference, the sharp edge which is coming between the two subtriangles.
See, if we were to use Groth shading and Fonck shading, what would that have done? In fact, smoothened the rendering. That's what it does, thereby removing the details. So, the whole purpose is lost. At one point you are trying to add details through subdivision, and when it comes to rendering them you just do the reverse process. Does not work. So, you would be actually using flat shading. Okay, so next, yeah, there is another. This is slightly better result than the previous one. So, perhaps previous was one of those the kind you would have generated in your assignment, but this is somebody else has done it. So, so here this was the base triangle, you can see that, right? And then these are all the perturbations added as this height during the subdivision. And what has been done is that this 0 height, or let us say the height at the base, is given a blue color, something like giving you an impression of water, and again in fact when you change this height you can vary the color. So, there could be different gradation of colors, it could be green to brown to whatever. Right. So, this looks reasonable. Okay. Now, in fact, there is okay. Let's talk about some other ways of doing this subdivision. So, one was this triangle edge. There is another way which you can use for subdivision is the diamond square method. What is diamond square method? Let us say this is the configuration you have at an iteration n. Right. So, these are the points given to you. Now, in the case of diamond square subdivision, this is what happens topologically. You obtain this point, which is the average of these 4 points. Similarly, you obtain this point, which is the average of these 4 points. This point average of these 4 points, and this point as average of these 4 points. So, there is a middle point for this square, which is the average of the corner points. And then you have this point, which is obtained from these 2 points. You have this point, which is obtained from these points. You have this point, which is obtained from these points, and so on. Right. So, what you sort of construct this shape on the top of this shape, right. So, these are sort of diamonds on the top of squares. So, that is why they are called as diamond square subdivision. Right. So, this is another way of doing the subdivision. See, one of the things which is some sort of common between this and the triangle H subdivision, that you end up getting points onto the edges here. Right. So, there is a point here, then there is a point here, there is a point here. Now, to retain the consistency which we had discussed, what might happen is that you may have some sort of an artificial edge getting appeared in the final structure. You see what I am saying? To maintain the consistency, because of the points which are being now created along this edge, you would see some lining on the final structure. Right. So, that is in some sense an artifact which may be there in the case of diamond square subdivision and also in the case of triangle edge subdivision. Okay. So, that is also referred to as crease effect. It is an artificial crease which is being formed, right, at the edge. So, in order to avoid this, there is another scheme of subdivision which is called as square subdivision. Okay. So, here what is done is you have again these points, let us say at an iteration n. So, what happens in the next iteration, that is what we are going to look at. So, this is what happens. Here we create these 4 points within this square, another 4 points within this square, and so on. Right. So, basically this square is in some sense getting replaced by this square, and so on, and these 2 squares are again joined. So, there is a square here, square here, square here. So, from squares you get squares. It's structurally. Now, how do you get this point? That is the question we should answer. So, this in fact is obtained using bilinear interpolation. So, let us say these are the 4 corner points we have, and we are trying to locate this point. Okay. Now, let us say I just enumerate that as 0 0, 1 0, 1 1, 0 1. Okay. So, this particular point is located at 1 by 3, right, and this particular point is located at 2 by 3, and so on. So, if I perform a bilinear interpolation, see, one pass in this direction, another pass in this direction. So, this point can be located in some sense from the weights which are shown here, right, like the weight of 9, 3, 3, 1, which are nothing but the coefficients, weight coefficients which one needs to apply to the respective point. So, this point is basically obtained as 9 times this point, 3 times this point, 3 times this point, and 1 time this point. Okay. Which you can further normalize, divide the whole thing by 16. Right. So, these are nothing but the, and in some sense it is all telling you the proximity of this point with respect to the 4 corner points, which is what happens in bilinear interpolation anyways. Right. So, similarly the corresponding weights would get determined for this point which you are trying to obtain here, and this point and this point. So, each of these 4 points now can be computed using bilinear interpolation from the corner points of the square. Fine. And once you have obtained this point, all the points of the square, then you have obtained a new configuration for the iteration n plus 1. Now, this can be again repeated. And if you want to preserve these boundaries, because what is happening is, in some sense I have now from this boundary I have reduced the boundary to these, right, and in further iteration I would come here somewhere, right. So, but if you want to preserve these boundaries, then you have to do something extra within this region. So, you can obtain extra points which would locate points here, locate point here, and so on. So, you have extra squares for the boundary cases. Fine. So, so in fact, let us say if I were to use this process of repetitive bilinear interpolation to a curve or to a surface in this fashion, like a subdivision, what is the limiting surface we have? See, if let us say if I were to use some sort of a midpoint subdivision, just take an example of a curve. Okay, maybe I can show it from here. So, what I mean to say is, this is the situation to start with. Now, I am obtaining a point here and obtaining a point here, which is the midpoint of the two. Right. Now, in some sense I have, so let us say I preserve the boundaries also. So, in some sense I have new set of points like this. Again I can do the same thing. So, what happens is this, right. So, what is the limiting curve I have? This is a subdivision we have seen, right, even of a Bezier curve. It's a quadratic curve, right? It's a Bezier quadratic curve, isn't it? We keep subdividing it, and then now here what we are doing is we are actually perturbing them. Right. So, this is topologically, this is what is happening, but then you are perturbing the heights, and that is what will create a structure like a terrain or a landscape. But this actually does not give you the artifact of creasing, because every time you compute these new points, so these points are not aligned to one of the edges, right. So, this removes the artifact of creasing. Fine. So, this was due to Given Miller, I think introduced in SIGGRAPH 86 or so.
But how do we ensure consistency in this case?
See, the consistency is, so what I am doing is I am computing the height of this from these guys. Similarly, height for this with the same weight structure. So, there is no issue there. Is it fine? So, it is basically 1 over 16 times height of this, 3 over 16 times height of this, 9 over 16 times height of this, 3 over 16 times height of this. So, there is no issue of consistency here. Okay. So, now some of the applications, well, we have seen examples of coastlines, we have seen example of landscape. In fact, this is a much better example now, right, which even has some fogginess to the atmosphere, right. You can also do clouds in a similar manner, where you in the case of cloud, what is it that you need to change is the opacity, right. It is the opacity which would determine the thickness of the cloud, right. You can even do candies, and in fact, the slides which I have circulated contains an example of candies. It is not candies, the internal of the candy, not the candy to eat, but the cover of the candy, which you can generate using a similar process. Also stones and many other things, right, plants, trees, which we have already seen. Okay. So, now the next, so these were random fractals, and we can see the relevance of these random fractals towards the modeling of natural phenomena. There is another kind of fractals which are also referred as algebraic fractals. So, you might have heard Mandelbrot's set or Mandelbrot's function, which is again some sort of a generating or a transformation function, z is equal to z square plus c, where z and c both are complex, they are both complex numbers. Okay. So, the idea here is when we are saying algebraic fractals, we are basically doing a visualization of this function, right, how this function iterates. So, for that there is a very simple algorithm. So, consider C to be, let us say, the point on the region you want to display. The fact that these are complex numbers, they can be written as something like x plus I y, right, which is the position in 2 dimensions, right. So, if I consider C to be the point in question for the region to be displayed and z naught given as an initial value to z. So, this is the function which I am going to use. So, there has to be some initial value of z, which I call it as z naught. Then all what is happening is the evaluation of this function, which is z n is equal to z n minus 1 square plus c, right. Then what you do is you examine the size of this z n, right. The size could be just the squares of the real part and the imaginary part. So, this is the size. So, what you are basically looking at is some sort of a divergence characteristic of this function, z is equal to z square plus c. So, clearly there is this self squaring which is happening to the function. One would imagine that this function would diverge so, right. But it turns out that there are points they never grow after a certain value, right. That is what actually gets defined as Mandelbrot set. Okay, so, here we are just looking at a mechanism of displaying this process. Okay. So, when we do the evaluation of this size, if the size turns out to be a tolerance defined by you, then you assign a color which is actually a function of this n, which is the iteration count, to this point C in the region. Okay. And if it turns out that it never grows after a certain size, that means you have crossed a certain limit of number of iterations you have assigned for, then again you assign color to that n, which is the limit of your iterations, right. So, this would give you the set of those points which stop growing after a certain number of iterations, right. So, that is what is the entire algorithm is all. Okay. So, the kind of structures you would observe is something like this. So, this is the start where you have a region starting from, let us say, minus 0.5 to minus 1.25 to 2 to 1.25. So, there is a radius of 2.5 region, okay, and you obtain something like this. So, and these yellow points are the points which do not grow after a certain number of iterations. Okay. And that is what the Mandelbrot set is. Now, the interesting point is, and that is where we would like to see this, the similarity of these fractals, the algebraic fractals vis-a-vis the other fractals we have observed, is that if you zoom in to the structure, see, if you take a small part here and try to zoom in here, this is what you obtain. Okay. So, by zoom in, what we mean is that you take a small region here, increase the resolution of your computation for the region C you define, and obtain this. So, this is what you get after zooming, and what you observe is that there are similar structures like this, which are of the similar shape which you had obtained at the first level from where you have zoomed. And again you can keep doing this process of zooming in. So, again you find details. So, there is infinite details to the structure, that is one observation. which is what is shared by the other fractals, and also there is a recurrence or reappearance of a similar structure which you had started with. So, there is this property of self similarity. Okay. So, for the purpose of looking at as a process of generating these patterns and structures, they are in the same category, right. So, that is what we are also looking at. We are perhaps ignoring the mathematics of this function, right. Okay. So, in fact, there are people who have attempted looking at the generalization of this, where z is actually coming as z to the alpha plus c. Rather taking a z square plus c, you consider some power of z, right, and this alpha could be an integer, it could be a real, it could be positive or it could be negative. Okay. And interesting patterns can be generated using this. Okay. And one characteristic which is observed is that if you define L as a lobe structure. So, let me go back and say that this is one lobe structure. Okay, if I say that this is one lobe structure, then the number of these lobe structure is basically given as the floor of absolute value of alpha minus 1. Okay, so, when I had alpha to be 2, then the number of structures I had 1. If I consider alpha to be 3, then the number of lobe structures is going to be 2, and so on. In the slides which I had circulated around, you can see there are patterns where a different alpha is considered other than 2, and you have these various lobe structures, right. And there is another interesting observation is that even the fractional part signifies some sort of a beginning of the growth of a small lobe structure, right, which is like a baby lobe structure. Okay, so people have tried other functions also. So, this is the book you have, Beauty of Fractals, full of such structures. So, those of you who want to have a look at it can take it and see it. So, just to give you the idea of this, I think the resolution is not so good. So, what do I mean by the these lobes are somewhere here. So, this is like I am calling one lobe, okay, this is another lobe, and so on. So, for alpha is equal to 10, you would have 9 such structures, right. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And even in the case of negative number, so this is alpha is minus 10, okay, and this is what I am referring to as a lobe structure. So, there will be 11 of such. Okay. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So, anyway, see, we are not actually looking at the implication of this number in terms of the mathematics behind it. We are just trying to display them. So, there are in fact very interesting properties with respect to what happens mathematically to these. So, one can take other complex functions and see this. and clearly this would not happen to all structures. See, there are only certain structures which would exhibit the property of self similarity and details inside. Okay, so there is a class of functions which would give you this, right. Okay, so let us stop here. Next time we will talk on something else. Maybe we will start animation.